Okay, with that, it's time to make a start. I'm just going to share screen here. Okay, and we're going to look at the energy balance in terms of the dynamics, so the multiplicity of steady states. And we'll also talk about the unsteady state mode of operation and then residence time distribution. So I was hoping to finish this one last time, but we didn't get to these questions, so we'll do that today. And then unsteady state operation, we don't actually have a separate tutorial for that. In fact, this set of notes does contain multiple case studies. So in effect, it's like a tutorial in its own. And then for RTD, we have tutorial 5. So we'll look first at the tutorial 4 questions, and then we'll take a break and then come to RTD. Before we jump into the questions, though, let's just talk about what we mean by nonlinear dynamics. So before we start with that, any questions or comments so far? So I know you'll want to know more about the test, but yeah, I think we can talk about that a bit towards the end. Yeah, it will follow pretty much the same format as the first test. Okay, can I take it as a given that you've all worked through the study guide and that there might be questions of clarity and so on, but largely you've worked through the study guide, right? Okay, I'll take that as a yes. Okay, so let's talk about nonlinear dynamics. So in nonlinear dynamics, quite often what we are trying to do is deal with the fact that our systems are often not linear. And when I say systems, what I mean is we can represent any process with a set of differential equations, and we can write the rate of change of the state of the system in terms of possibly the time and the system variables themselves. So the variable y might be the concentration and the temperature and the pressure and other things like that. So in reaction engineering, quite often we take that y to mean the temperature and the concentration. And quite often in engineering, or not often in engineering, but in terms of what you've seen in most of your courses so far, your variable y was something that you solved for. So quite often you said, I'm really interested in steady state. So you set that to 0, and then you solve the right-hand side of the equation, and you solved for a value of y at steady state. And we've done some of that in this class so far. We've talked about there's a certain constant or conversion that we are solving for, and so on. Now, all that is fine until you encounter the situation where you possibly have more than one solution. So when you are searching for a steady state, it's often the case, in fact, it's generally the case that there's more than one solution to y. So there may be multiple steady states available. And in these notes, this is shown in terms of this example, right? If you imagine that you've got this the situation where there's a hill and you can position this ball at different positions there. So you could, if you give a small disturbance to this ball, in other words, if you kick the ball to some extent, right, to a low extent, then it will travel forward and then it will fall into this valley. So in the transient, it may roll up the hill a little, roll back down, and go back and forth a little bit until it settles down at the bottom of this valley. So we can think of that as one steady state, where the state variable is the spatial position. If we kick the ball hard enough to go over hill B, then it may make it into valley A, and so again, it may go up for a bit and oscillate a bit and then come back down and settle in here. So that's a different steady state. And there is another steady state right at the top of this hill. And it's hard to imagine that we can kick it there and it will stay there. But if we walked to the top of this hill and just placed this ball there, and if we placed it just right, then it wouldn't fall left or right. It would stay at that position, right? If we placed it just right. And so in this system, we actually have available 3 different steady states. And that's generally true. Any system may have multiple steady states. And so where we end up is a function of how we operate the system, right? In the context of a reactor, the way that we operate that reactor, right? The values that we apply, right? So design type variables like how big we make the reactor, what's the inlet temperature, what's the inlet feed flow rate, all those things go to determining which steady state we might fall into if there are multiple steady states. And we'll see something that's quite directly like that. Another thing to notice here is that you have different types of steady states, right? There's a certain zone of stability in A and C, right? If your ball has fallen to the top, to the bottom of A or C, and if you apply a small kick to A or to the ball at A or C, the ball may travel for a little while, but it will eventually fall back into that steady state. So we call those stable steady states, right? So if you are in a steady state, and if you disturb your object in that steady state, so it may get disturbed temporarily from that steady state, but if it comes back to that steady state, then we call that a stable steady state. So A and C are stable steady states. On the other hand, you can see that if you position the ball at the top of hill B, and if you apply a small disturbance, then that ball is not going to stay there. It's going to fall either into A or into C. So B is an unstable steady state, right? You don't have a margin of stability here, whereas you do for A and C. So you've got possibly multiple steady states, and then you've got different types of these multiple steady states. And so far in the coursework you've seen, the assumption has been that there's just one steady state and it's a stable steady state and you can operate at that steady state. So now we are being introduced to this idea that we possibly have multiple steady states and there might be stability issues. And then here in the notes, there's just this example showing that if you have a system of equations, and this one is taken for an oscillating spring, but you can easily imagine that you get a system of equations like this. So for example, in our reactors, if we were writing the balance on our species, and let's say this was the balance for mass, and so this was dx dt, and this was the energy balance, and we had dt dt. Then if the right hand sides here had any nonlinearity, so let's say instead of this linear case, let's say it was nonlinear, even if it was just x1 squared here, then we would have multiple steady states, and then we would be concerned about whether we are stable or not in those steady states. Right, so that's the issue that we are talking about here, the multiplicity of steady states and their stability. Right, any questions or comments so far? Okay, so we are going to apply this now in the context of our Cstr and our energy balance. So let's talk about the steady state in a Cstr. So we know for our Cstr, generally speaking, for steady state, we can write this balance, right? So we've derived this a number of times now. So we take this as a given for a Cstr steady state. And then we've also shown for the energy balance that at steady state, we get a balance like this. Right, so taking into account that operation, in fact, it's useful to have a little picture available. So let's draw that here. So if we have our Cstr, with a flow in and a flow out, And let's say we have our little cooling jacket that's trying to maintain our temperature in that Cstr. And then we've got some little coolant flowing around through that cooling jacket. Right, so that's our situation. And we, of course, want to run this reactor steadily. So we would like to have a steady conversion of our component, and we want a steady conversion, and we want to maintain a steady temperature in that reactor. So there's the temperature in the reactor here. We can also define, we know, a temperature in the cooling jacket, right? And obviously that temperature has to be different if we expect to have heat transfer. And then another important variable will be the inlet temperature here, T in. Right, so those are the three temperatures that we'll see just now are important to us. Right, so that's our situation. And we have this energy balance and we have this material balance. Now, if we look at this, this energy balance, we can see that our FA0X can be replaced by RAV, right? Because we would like to rewrite this energy balance purely in terms of temperatures. So we'd like to get rid of the material balance influence, right? So we want to get a nice version of the energy balance that lets us just think about temperature. So the first thing we can do is make the substitution for RAV. And it's still dependent on the concentration, of course, and just because it's hidden behind this RA. So let's try and unpack that further. Well, actually here I see in the notes before we did that, we just introduced this factor kappa. And this doesn't have, well, it does have a meaning, but for now, we just treat this as a convenience thing. So we are just introducing this variable kappa to help us group some of these terms. So using this kappa, you can see here that if you remove this sum theta I CPI, if you remove that as a factor outside the square brackets, then you'll end up dividing by that factor here, and then you've got T minus T in here. And so your kappa becomes the factor that will end up sitting in front here. So you'll have kappa times T minus TA. So you've grouped out that factor there as the kappa, and then you've grouped out this theta I CPI sum out here, right? So that's nothing but grouping. And then the left-hand side stays the same. We haven't done anything there. So with this balance, then if we look at the left-hand side of the equation, we will we actually won't do anything further here. We will simply think of this as the energy or the thermal energy that's generated by the reaction. Right, we know energy is not created or destroyed. It's a conservative property, and that the reaction only translates energy from one form to the other. So if you like, before reaction, you had a certain amount of thermal energy, right? Your fluid had a certain non-zero Kelvin temperature, and it had, if you like, a kind of chemical potential energy. So just the fact that you have molecules that have a certain structure, there's a certain amount of energy or enthalpy in that. So you've got thermal energy and chemical potential energy. And then the reaction itself will convert that to a different, in fact, let's try and write that a bit, right? So before reaction, you have a certain amount of thermal energy. So let's call that ET1. And you have a certain amount of chemical potential energy. So C PE1. Right, so the sum of your thermal energy and your potential energy must be the same before and after. So ET2 plus EPE2. Right, so the reaction is going to change the way the energy is distributed, right? And so when we think of this term, it's not that we are saying it's creating new energy, but just that it is giving us some thermal energy. It's translating chemical energy into some thermal energy. So although the notation is written as if this is energy generated, we can read that as heat generated and heat removed. So far we are talking about heat generated. So thermal energy, that's a result of the reaction itself, right? That's how we can think of GT. And note here, there's no reason to do this so far. We are just proposing to do this. So for now, we are just saying, let's say we interpret this as the thermal energy given to us by the reaction, right? And then on this side of the equation, we can see terms. In fact, we need to look maybe a bit earlier on. We can see terms here that relate more to flow, right? So this has more to do with the flow of energy through that reactor. And this has to do with the heat exchange with the jacket. So this is the adiabatic heat and this is the flow heat. So this side of the energy balance tends to change the temperature just by virtue of the fact of things moving around, right? Fluid pumping through the reactor or a thermal medium pumping through the jacket. So if you like, flow energy. And then what we are doing here is considering that to be heat removed. So there's the heat of reaction. So the reaction is tending to release thermal energy. And we've got flow energy, which is tending to give us, tending to stabilize the temperature in the reactor. And we got all these from the same energy balance. So in effect, we are just saying call the left-hand side G and call the right-hand side R. And both these come from a general balance. You'll see that the rate of change of energy is GT minus RT, right? So if you go back to your original balance, you'll find that you are in effect writing here dE dt equals G of T minus RT. Okay. Okay, any questions or comments so far? Okay, so we are just representing our energy balance slightly differently now. And we can further simplify our G expression if we look at a specific reaction. So given a first order reaction, we know that our reaction rate will become Kca, and we can rewrite that Ca part as Ca naught times 1 minus x. And then if you, in the numerator, if you rewrite Fa naught, so your molar flow rate as the volumetric flow rate times the volume, then your concentration can cancel and you'll be left just with the volumetric flow rate. So apologies for the symbols. This is supposed to be the volumetric flow rate here, right? And then you've got, in effect, you've got a volumetric flow rate here and a volume there. So you can divide volume by volumetric flow rate, and we know that's the space-time, right? So we have established earlier that tau equals V over Q. In this case, we are writing it as V over V naught. Right, so we'll get a tau there. And then if you multiply that out and regroup it, you'll see that you can rewrite your conversion in this form. Right, so you've got conversion as a function of space-time now. So by virtue of the fact that if we have specified the order of the reaction, we can rewrite the volume in terms of the conversion like this. And so that's what we do. So our G of T, we rewrite it in this form. Right now, this is useful to us because our Ks are functions of temperature only, right? Our kinetic rate constant is only a function of the temperature. And our space-time, if we regard that as a fixed value, then that's going to give us only temperature as the variable of interest in this function. So we have now managed to convert our material balance side to a single variable function, and that means we can plot this function easily. So if we go back to our drawing here, we can we can then draw out G as a function of T. And we'll see just now that if you do plot that out, you get this kind of curve. If it's, I think this is for exothermic. Right, so, and you can try this out. So you can take some of the examples you've seen in the previous tutorials and try out for different, you can try delta HR being positive or negative. What does G of T look like? So in other words, you can just unpack K. Remember, K you can express in terms of the Arrhenius expansion. So K equals A times e to the RT. Sorry, K is A times e to the minus e over RT, right? So you are applying this Arrhenius expression for all these Ks, well, for these two Ks, and then tau you are taking as a constant, take something simple like 20 minutes. And then this heat of reaction, even if we assume this is approximately constant, so we take some constant heat of reaction, just by virtue of the fact that you've got this expression here, you've got a temperature function here and a temperature function there, you'll find that you get a function that looks like this. And in fact, if you think about it, you can see here that for K large enough, when K is very big, then this term in the denominator, this tau times K, this becomes much bigger than the 1. And so it's basically, okay, let's write it out here. So you've got tau times K over 1 plus tau times K. And and then if you take large values, so large values of tau times K, then that's going to give you that this becomes approximately right. So large values of tau times K means it's much bigger than 1. So it's approximately that, which equals 1. So that means as these values get bigger and bigger, 1, then this becomes a constant, right? So it becomes equal to the heat of reaction itself. So in other words, for this graph, you can actually say that we know the upper limit here. It's going to be the heat of reaction. On the other hand, if we consider very low values, so for very low values of tau K, you can say this is approximately 0 over 1 plus 0, which is a 0. So the lower limit is a 0 and the upper limit is the heat of reaction. And in between it goes through that kind of curve. Right, so that's our G of T. Any questions there so far? Right, and then now let's think about drawing R of T. So if you look at your R equation, if we take the heat capacity as approximately constant, and if we know that the inlet flow ratio is constant also, right? And when I say constant with respect to what variable, of course, it's with respect to temperature. So we know heat capacity is a weak function of temperature. So that's why we have to make an approximation there. Our inlet molar flow ratio, that's up to us, right? That's our design choice. So that's definitely not a function of temperature. Kappa, we have to unpack that. Let's see our kappa definition. So kappa, your heat transfer coefficient between the jacket and the reactor, that may be a weak function of temperature. If you think back to your heat transfer course, you did have some weak dependence of that on temperature itself, right? We did try to separate it from temperature because we wanted to use it as a coefficient, not as a function of temperature, but we had some weak dependence, but let's say it's approximately constant. The area, of course, is not a function of temperature, right? We are not worried about thermal expansion and things like that. So we take area, and it's really very slow. It's not going to change area much. And then here, as we said already, those we'll take as weak functions of temperature also. So kappa is approximately constant in T as well, right? So kappa is constant in T, that's constant in T. So you have a nice stable coefficient for T, a nice constant in front of T. So R of T is going to be a straight line, right? The T inlet, that's not changing with T. That's, again, our design decision. We can choose our inlet temperature. That's not going to change as the reactor temperature changes. And then the jacket temperature, we assume that is approximately constant. That is more of an assumption because here in the jacket, we know that the jacket temperature does change as as we get heat transfer between the jacket and the reactor. But an approximation we've been using already is that this jacket fluid is flowing so fast that its temperature doesn't change that much. And typically in industry, if you have something like 20 degrees and if you use a high enough flow rate, maybe it's coming out to 22 degrees as it absorbs heat from the reactor. And we regard that as approximately constant. So we are taking this as a temperature constant as well. So in other words, you have a constant intercept here and a constant gradient there. And then R of T is a nice straight line with respect to T. So R of T looks like this. Let's draw it like this, right? And we can move it around. So this is R of T. Okay, now if you look at what we have here, and if you think back to what we said right here, right? And of course, the energy in the reactor, that's a function of temperature. So we are saying that the temperature, we are saying in effect, right? And here I'm being a little bit imprecise. We are saying the rate of change of temperature is related to, right? In fact, it's not, I'm using the wrong symbol. It's not approximately true. It's conceptually approximately true, okay? So let's make a conceptual symbol here. So dt is conceptually positive when G is more than R, right? So when the reaction is giving off more thermal energy, then our flow terms are taking that energy away. That's how we are reading our energy balance now. Any questions on that? Right, so if that's the situation, let's think now about what's going to happen in our reactor when we apply a certain starting point. So let's say we start our reaction at this temperature. So let's pick this as a T0, a T01, if you like, right? Because we'll consider multiple initial temperatures. So with T01 sitting there, let's see what's going to happen, or let's imagine what's going to happen. So here's temperature and here's time. Right, and we are using a T0 value here, so it's a fairly low one. Now, if we look at this equation, or if we look at these lines, you can see here that at T01, the removal rate is greater than the generation rate. So that means we are on balance, giving ourselves a negative dt. Right? On balance, our system is tending to move in this direction. Right? dt is negative, and remember, on the x-axis is T. This is the reactor temperature. So we are plotting against the reactor temperature here. So in this region, dt is negative, right? And that's purely because of this, right? dt is proportional to GT minus RT. GT is less than RT at this position, right? So here, GT, the red line, is this value, and RT is this value. So GT minus RT is a negative number. So dt is negative. That means we are moving to the left here. So our temperature is going to go down. So it will go down like this until it reaches this value. Right, so let's say that value was given by this. So let's say that's there. Now we are going to then our temperature will go down until we get closer and closer to this value. And let's think about what happens at this value. Let's give it this color. So at this value, let's imagine that somehow our temperature went even below this value. So let's say the temperature somehow went here, right? So if the temperature was here, then suddenly you see G is greater than R. So if you go below this point, you will have dt being positive, and it will push up towards this value, right? If you are beyond this point, you can see R is greater than G, and you'll fall below. So this is what we understand as a stable steady state. So we had SS for steady state before, now we have SSS, right? Stable steady state. Because if your temperature goes a bit higher than this temperature, then the system will force it back down. If your temperature goes a bit lower than this temperature, the system will force it back up. So that's why this is a stable steady state, right? So that's so we can imagine then that if we have other starting temperatures, it's not going to be so easy for me to write here with this mouse, but they are all going to do this kind of thing, right? And like we said, if we start below this value, then they'll all fall up to that value. So any lower temperature then, and let's call this temperature T1. So this is T1 here. T1, okay. Now let's think about this other temperature. Let's call this temperature T3. And you can see here T3 is a larger temperature than T1. So we'll draw T3 up here. So T3. And let's just draw a line for T3. Now let's think about what happens when we go to temperatures above T3. So if our reactor, if we somehow force the temperature in our reactor to be a higher value than T3, then you can see R is going to be bigger than G, right? R is this kind of purple line and G is the red line. So R is greater than G. So on balance, our temperature will be dropping. So it will do that. So if we start at a higher temperature than 3, the system pushes us back to T3. So that will happen there. And then if we start at values lower than T3, then G is bigger than R, and we are pushed up in this direction. So below T3, in the immediate vicinity, our system is changing like this. And these are all trajectories that could be happening in our reactor, right? So all this, these lines that we are drawing here, this is a scenario where we've started the reactor at a certain initial temperature. So we've started at this initial temperature, and we are tracing how the temperature is changing with time. So if we are watching with our little stopwatch, we are watching how the temperature is changing with time. It will be changing according to that line shown there, right? So those are some trajectories that we can anticipate here. And then there is a third temperature here, which we'll call T2. So here's T2. And you can see T2 is in between T1 and T3. So let's draw T2 here. Now let's see what happens when we go just above T2. So just above T2, you can see G is bigger than R. So the temperature gets pushed in this direction away from T2. And then just below T2, you can see R is bigger than G. So on balance, we'll be removing thermal energy, so the temperature will drop like that. So that's why we call that an unstable steady state, right? The moment you go above T2, and this is T1. The moment you go above T2, you will be pushed towards T3. And so it's nothing but a continuation of these lines. And I should show this curving in. Obviously here, our driving force is going towards 0. So it takes an infinite period of time to actually get to T3. We never really get to T3. So any temperature, any starting temperature above T2 does that. And then, as we said, any temperature below T2 will fall to the lower steady state. So you can see on this picture then, we have two stable steady states, right? T1 and T3. So all orbits in the, all trajectories in the vicinity of those two steady states will fall into that steady state. And then T2 is an unstable steady state. All trajectories that start near T2 will be pushed away to one of the other steady states. Okay, any questions or comments there? Okay, now we'll be looking, when we get to the tutorial example, we'll be looking at how we chose to draw this particular line. So we just said, okay, let's put down this line, and we went ahead and we drew that picture. So let's look at this line and what's behind it. And for that, all we have to do is look at this equation. And in this equation, we said, yes, we have this as the slope. We can see this is the factor in front of t. And then for the intercept, it's this thing times this thing, right? So our intercept here is influenced, we can see, by the inlet temperature and the jacket temperature and the heat capacity. We can't do so much about this, right? The reactor contents, the reactants and products, we can't really choose the heat capacities there. We could choose to add an inert to the system. So if we wanted to fool around with the gradient of the line, we could think about adding an inert and doing things like that. But besides that, we have the inlet temperature that we can play around with that moves the intercept. And we have the jacket temperature that also moves the intercept. So we can see that we can quite easily move the intercept. We can shift this line horizontally as we change our inlet values. So let's say we do that, and let's say we pick an intercept that leads us to this, right? So we've changed T in. T in doesn't change the slope of R, right? So R is going to be the same after that. And now we see we have only one steady state available, right? Before we had 3 steady states. Now, just because we shifted our inlet temperature, we suddenly only have one steady state. And we do have to think a bit about what type of steady state this is. And towards that, let's draw it as the kind of cooling color. And so R is the cooling, well, not cooling, but thermal energy removal. Oops. And the red one is the generation. Right, so we can see here that it is a stable steady state. So if we go above this steady state, right, let's try it. So looking at this point, if we were to go above the steady state, the system would return us back to that steady state. If we go below the steady state, then G is bigger than R, and it would push us towards that steady state. So it is a stable steady state here. And we can do the same thing on the other side as well. So if we were to shift our R such that it was like this, so we changed T in, and we now found that we had we now found that we had this new steady state that was here. Then if you compare G and R, then you'll see that this is also a stable steady state. So that sounds nice. It sounds like, okay, we'll have a nice nice stable steady state, and there's only one, so it's much simpler, right? But that might be problematic for us. What if it's not a steady state that we want? Right, so let's say it was this lower steady state. So there exists some choice of temperature where we are going to fall down to the steady state. And we possibly don't want that lower steady state. We possibly are concerned that operating the reactor at too low a temperature gives us a bad reaction rate. And so we have to be aware of whether we are falling into that trap. We have to know that this lower steady state is what we are going to fall into if we apply an inlet temperature which corresponds to this line, right? And inlet temperature doesn't show up directly on this plot, right? T in is a little bit hidden behind. It's not exactly an intercept here. It is related to the intercept, but you can't read it directly off this graph. So for a certain T inlet value, we will end up at this lower steady state here. And for a certain other T inlet, we may end up here. And it might well be the case that there's a material limit. So it might be that this is the material limit of the reactor. And if we didn't know that that T inlet value, right? Maybe T inlet is some number down here. We didn't know that using this T inlet would cause us to have this steady state, which is beyond the safety limit of that reactor. Then that's going to happen. So you see the importance of being able to construct this picture. It helps you understand where that reactor is going to end up operating. That helps us test the constraints. It also helps us just understand the operation of that reactor. Is it operating at the temperature I expect it to? And in fact, what's revealed here is some kind of sneaky values, right? So there is a critical value where this happens. It's so easy to make a parallel line. Let's see here. Yeah, I can move it. There we go. All right, so here we have a critical value of T in, and in fact, we have also a critical value here. So that's hopefully you'll say that's parallel. So there is a certain T inlet. So behind this line, there's a certain T in where it is just going to the case of one steady state. So Ti, let's say A. So this is an inlet. So behind this line, there is a particular inlet temperature where our system is just transitioning from 3 steady states to 1 steady state, right? If the T inlet value is slightly lower, then this whole R line would shift a bit to the left, and then you'll have a steady state here, steady state here, steady state here, right? And so this is the point where just past this value, we only get 1 steady state. Now, let's say we were trying to operate at this low temperature, and we were close by this value for T in. Then a slight fluctuation in your inlet temperature will cause the system to run away to this high temperature here. By the same token, if you were operating T inlet at a value corresponding to here, and you didn't know you were so close to this critical point, a slight fluctuation in your temperature. It might have been just 2 degrees colder on that day. And then you'll suddenly find that you are just to the left here, and there's only this lower temperature, much lower than you want to operate your reactor. And you'll find no matter what you try to do, you can't move that reactor for long away from the steady state. It's always falling back to that steady state. So we call these ignition and extinction points, right? So this we call the ignition point because when you go just past this temperature, you only have available the high temperature steady state. So the system, if you like, ignites and pushes you up here. And then this is extinction, because the moment you go a little below this temperature, the system falls down to that value. So this is the extinction point. And if you've been reading around on nonlinear dynamics, we call these bifurcation points. So bifurcation, it means split in two. It means go in 2 different directions. The 2 directions here being that on the one hand, you've got 3 steady states here, and on the other hand, you've got 1 steady state. So you are kind of at the crossroads. You go down one path, you've got 1 steady state. You go down the other path, you've got 3 steady states. So bifurcation. So this is a bifurcation point, right? The values behind this black line are a bifurcation point, and behind this particular black line, that's a different kind of bifurcation, right? So these are all the concepts that we have now. We've got multiple steady states. We've got stable and unstable steady state. We've got bifurcation points, right? Going, switching from one set of steady states to another set of steady states. Okay, any questions or comments there? Right, so that's the idea, and you'll find that there are other things you can think about. So work through the notes carefully. You'll see it talks about the parameters that affect the shape of the curves, and so you'll see that because our heat of reaction, that's our eventual value. As we consider different heats of reaction, then that shifts the curve around as well. You'll see that tau does affect G, and then R as well. So as you increase kappa, this line becomes sharper and sharper. And also the inlet temperature, you can see the inlet temperature does shift the intercept, as we said earlier, right? So we can influence these lines. So this is a very, if you like, meta view of our process. So we might be more familiar with talking about we want to get to this conversion or that conversion, and those are kind of very direct variables. But behind all that, behind the way the system is influenced, behind the pulls and pushes on the energy in the system, we can do things. We can choose gradients for these lines that help us stay a bit further away from these critical zones where we are suddenly switching from one mode of operation to the other, right? As chemical engineers, we don't like that. We don't like surprises. We don't like operating close to regions where things can switch suddenly from one state to the other. We like our equipment to be sitting peacefully and doing the same thing for years and years. So we regard those as dangerous points that we want to stay away from. And as you see, through the energy balance, we can discover where those regions are, and we can design a nice, safe system around that. Okay, so that's the idea. And then here, this picture, this is actually quite a nice picture directly in your textbook. So if you consider different initial or inlet temperatures or different jacket temperatures, then you get all those straight lines there. And then you can see here, this table summarizes all the steady states and so on. So you can see if you've got TI1, so that inlet temperature only has that one steady state there. And then TI2 has 3 steady states. So you've got you've got 2 steady states, 2 and 3. So 2 and 3. So it's a bit of a not salad point, a bit of a saddle point. and then TI3. So if your inlet temperature is TI3, then you've got 4, 5, and what is that? 9, I guess, 6. So 4, 5, 6, and then and so on. So it gives you a nice summary of all that. And if you plot it again a bit differently, so instead of plotting it against temperature, if you were to plot it against inlet temperature, then you can also see that. You can see at this inlet temperature, that's the steady state temperature. And then past a certain inlet temperature, you've got the 3 steady states. This dotted line is your repulsor steady state. So you've got the 3 steady states, and then past a certain value, you've got the 1 steady state again. I didn't explain that term earlier, a repulsor. So an unstable steady state we can also call a repulsor. So this point here, which we called an unstable steady state, we can also refer to it kind of more emotionally as a repulsor. It repels everything away from it. It's a repulsive steady state, repels everything away. These are attractor steady states. They are attractive to the system. The system tends to fall into them, right? So repulsor steady states or unstable steady states, and attractor steady states or stable steady states. You'll often find in chemical engineering, we have our own set of terms, and in pure maths, we have our own other set of terms, and they are the same thing. They are just expressed differently. Okay, so we can look at the tutorial around this. So we have a nice tutorial question. You can read here about finding those points. So you can analytically solve for those bifurcation points. If you realize that the point of bifurcation, right, the point where bifurcation arises is where this R line is a tangent to this G line. So if it's a tangent at this point, their gradients are equal and their values are equal. So we can find the gradient of G. So we can take dG dt, and that will equal dr dt. So the gradients are equal, and then the values are equal as well. So G equals R. So that's all that's shown here. We figure out how to get dG dt here. And then dr dt is obviously much easier. And then we also say G and R are also equal there. And then if you follow that, you'll see you have a nice easy criterion, a way to find that critical bifurcation. So, and there are 2 bifurcations, obviously. So you can solve this equation and you get your 2 temperatures there. Okay. So let's look at the tutorial question around this. Wrong one. Tutorial 4. Okay. So we've done the majority of these questions last time, right? We drew those isorate lines, and we navigated the reaction plane and all those things. So we are just skipping to the G and R type problems here. I guess here's one. Right, so in this problem, we have a Cstr complex reaction. We are concerned about temperature going beyond the safety limit of 600 Kelvin, right? So that's a problem we want to solve. And then it says data is available, but I've made it easy for you in this problem. I've given you a gradient. So dr dt is 80 joules per mole per Kelvin, right? Joules per mole, those are the units of R, and then this is dr dt, so that's per Kelvin. It's also known, kappa is for, this should be a kappa, sorry, I've got a K here. So it's known that kappa is 4, and your jacket temperature is also known. So this TA, so that this part is basically saying you can work this part out. And then your heat of, so that's just giving us the equation. And we want to know, when does the system reach the danger temperature? And on the next page, we are given the curve for G. And you'll see here that this G is a bit different. It doesn't follow the shape that we said the shape should follow. That shape was, that shape we showed earlier was purely for a CSTR with the first order reaction. And this problem did say it's some complex reaction, whatever that means. So we don't have first order, but whatever we do have, it eventually gives us this G of T curve. So you don't have to derive the G of T in this case, it's just given to you, and you're also given the gradient. So let's see if we can use all that to answer the question. So I'm just going to copy this figure. And let's make a new space here. Okay, so that's our figure. So now we want to plot dr, we want to plot r of t. So we've got g of t here. So this is g, this is g, and we want to plot r. So dr dt is 80. So let's take delta t of 100. So dr dt being 80 means that if that's 100, then r will increase by 80 times 100, which is 8,000, right? So if we start here, let's say, then we want to go 8,000 up. And if you look here, this y is times 10 to the 4. So going up from 0 to 1 is 10,000. So a value of 8,000 is somewhere here, right? So we can say this is the line that we have, right? So once more, if we take 100, so our gradient is 80 Rs per Kelvin, if you like, right? I'm just making nonsense units, right? So, sorry, 80, right? Not 800. I'm just going to cross it. So 80 R per Kelvin. So for convenience, let's just take 100 Kelvin. So 100 Kelvin times 80, that's 8,000, right? And then if we look on our y-axis, that's in units of tens of thousands, right? 10 to the 4 is 10,000. So 0 to 1 is 10,000. What we want is 8,000. So 8,000 is about there. So if we are starting here, then the line goes like that, right? So that's our line. And we can just draw it like that. And now we are also given the specifics about the rest of the equation. Oops. Show what's happening here. Okay. Okay, so we are given the other values. So we are given the temperature in the jacket. Oops. We are given the temperature in the jacket. So we have TA, and we also have K or kappa. So we can get a number here. Right, so we can get a number here, and we have this, well, we have the gradient. So 1 plus kappa times this thing here eventually gives us the 80. So we have this part of the equation sorted out. Actually, you know, to really do this properly, you do have to calculate what this factor is. And you can use the gradient for that. So in fact, let's copy this out and let's show how to do all that here.
Question and then I'll leave. I promise it's true. I'm telling you the truth.
Sorry about that. So we've got this equation here, and we want to look at a way to plot this. We want to get that intercept. So to figure this out, and we've got the gradient. So we can see just from this equation that, let's write it here, dr dt equals, and so the gradient here is going to be some, and I'm not going to do this perfectly, just the idea, right? So this term times 1 plus kappa is our gradient. So times 1 plus kappa. And our kappa value is known to us. Well, let's not overwrite this. So let's do that here. So we can say dr dt is known, that's 80. And then kappa is a 4 given to us in the question. So just 80 divided by 5, right? So 1 plus the 4. So 80 divided by 5 is equal to our sum theta CP, right? So that's 80 over 5, right? So our function, so we can get this exactly. So we can write here RT equals, and this is going to be 80 over 5 times times 1 plus kappa, so 1 plus 4 times T minus T in, and that's given in the problem, I think. Yep. Yeah, no, that's the jacket. Well, that's what we're trying to find, right? We're trying to find T in. What we have is the jacket temperature 400 Kelvin. So we've got this T in, which is unknown to us. And we have kappa, which is 4, and the jacket temperature, which is 400. And so with this, we have an equation of a line, and we don't know the intercept as yet. But we can, we have a criterion. We know that we don't want to exceed this 600 Kelvin. So we know that the maximum temperature we can tolerate is 600 Kelvin. So now we can actually use that line. Is this the right? So here's our 600 Kelvin. So we don't want to violate this temperature. So let's draw a line through this, which is parallel to the first line, right? And that's basically our on the limit that we can tolerate, right? So this is the line that that determines. This is the line where we are just running foul of our safety concern. So the T in value that we look up then is this one. So we can read off this value. So this is about 480 Kelvin. So we can say that at a temperature of 400, let's do a new one. So at a temperature of 480 Kelvin and an R value of, and we can read off here, that's a 0, and an R value of 0, we can calculate T in. And in fact, that's it. It's as easy as that, right? And in fact, I think when I put this problem up, I was trying for something where you actually had to look for the tangency. You wanted to know when it was going to run away. But in this case, according to the gradient that was given to us, we weren't actually going to run away. Even if we ran away, right? Even if we went past the ignition point here and we ran away to this temperature, we were still well short of, well, not well short, but we were still short of 600 Kelvin. So even at the ignition point, right, which is here, even at the ignition point, which is something like this, we are still at about 570 Kelvin. So we're still okay even at ignition. If you like, there is a different kind of constraint here. If we had an inert and if we were making the line shallower, maybe the problem would be a bit more interesting. So if our line was shallower like this, then we would be concerned that, yes, we are exceeding that. So if the moment we go past the ignition point here, we would fall into the steady state. So in that case, we would shift this line and we would say, we can only operate like this. We can only try to operate in this region where the maximum steady state would be here. So if we go, if our temperature went lower than this, then all our steady states are below 600 Kelvin and it's all safe. But the moment our line is such that we are going to this here, then there does exist a steady state that is beyond 600 Kelvin, then that danger has not been avoided. So that would be a bit more of an interesting question, right? Currently, the way it's posed, the 600 Kelvin, that directly tells us what our T in is, and we can calculate it quite easily there. Okay, any questions or comments on that? Let's see, what are the other, so what concerns would you have in operating at the lower temperatures? Right, so at the lower temperatures, of course, your reaction rate is much lower, right? That's generally true, whether or not it's reversible. All reactions are lower at lower temperatures, right? By the end of the day, all the molecules are moving slower. There are fewer collisions. There's a lower reaction rate at a lower temperature. So that's our concern at the lower temperatures. Of course, there are extreme low temperatures where things get brittle and there may be failures for extreme low temperatures, but that's not really what we are talking about. You don't really get that very commonly. So anyway, we are worried about killing the reaction at the lower temperatures. So what's the lower limit on the inlet temperature in that light? So I guess in this case, you would simply be looking for what temperature would cause you to go below this. So at what temperature? Well, actually, that's here. Let me just draw this again. So here's our line. And so if we go below this temperature, so we can consider this extinction point now. And now that we've identified the extinction point, and because we have the gradient, we can just go down here to the intercept again and find the T inlet value. And then we can say, at T inlet values below the one corresponding to this line, we only have available these low temperatures as steady states, right? Our temperatures cannot remain for long above, say, 370. That might be very low for our reaction rate. So we might lose productivity at these low temperatures, right? So that's how we can navigate this plane. We can figure out where the rate is too low, and then we have to concern ourselves with where our material constraints are. And so the best operating region is somewhere in the middle here. So we need to figure out where among all of these is our feasible operating region. So that's our typical design type question. What are the inlet temperatures? These are the attractive inlet temperatures to us, and how are we going to stay there? So that question, how are we going to stay there, we explore in more detail in the 4DC in the controls course next year, right? But for now, in this course, we can at least identify regions where we want to operate, and we leave the problem to how to control ourselves onto there for later. Okay, any questions on that? Right, so that's basically how you do these problems. Also, do be able to sketch out your proposal of what would happen in the reactor. So if I ask you, if I give you a starting point here, what's going to happen? So you must be able to figure out what these curves look like, and It's expected that you are not going to draw these exactly. Obviously, you need to actually integrate the dt to draw this curve exactly, but you can at least sketch it, right? So in the light of the available steady states, you must be able to say, I think it's going to eventually fall from here to that line and so on. All right, so that's that class of problems, right? The energy balance. Let's see, there's a question. So where the red line that intersected the x-axis came from. So the question is, where did, let's see, that intersected the so am I looking at the right figure here, Zoera? The red line that intersected the y-axis, this red line, the G of t line. See, you mean here? So where did the flat red line come from? So so this red line, I was just saying that if we were to, I was just talking about a possible different question. So in terms of the question that's given in the tutorial, this flatter red line, this is not there, right? This red line is not in the question, but I was just talking about a possible other question. So if the line were flatter, then that 600 Kelvin, which in the current problem, the 600 Kelvin is not really an issue, right? It's not, we don't reach 600 Kelvin with the current ignition point. And then I was just trying to create a problem where we were going past 600 Kelvin. So if R is flatter, then you can get to 600 Kelvin. And then I was just talking about what we have to do in that case. Is that all right? Okay, no problem. All right, so so that's that question. And I guess that gets us to the end of that tutorial 4 of the 2 weeks ago. And then let's now look at this unsteady state operation. So unsteady state operation. So in our reactors, we've been talking about isothermal and then non-isothermal. And so you see, we've been progressively relaxing our assumptions. We started out with the most restrictive case. We started out with steady state isothermal. Then we said, okay, let's let the temperature change. So it became non-isothermal. So that was one assumption we relaxed. And to do that, we had to incorporate the energy balance. Now we are also saying, let's also consider unsteady state. We had unsteady state for the batch reactor, but now let's also have unsteady state for all the reactors. So we have unsteady state non-isothermal. So we have to go back to our energy balance, and now we have to retain our dE dt term. And we have to think about how to unpack dE dt. So before, when we derived this energy balance, we put a lot of work into getting away from E on the right-hand side, because E is kind of abstract. It's written in terms of chemical potential. We want it in terms of enthalpy, right? If it's enthalpy, we know we can take Cp dt. There's nice, easy ways to get numbers for these things. So dE dt, we don't know how to deal with, but then we go ahead and unpack it in terms of internal energy. And then we know we can rewrite internal energy in terms of enthalpies and pressures. So already this is easy now. Now we know we can get numbers for enthalpy through Cp, and pressure and volume, those are easy. Well, this is molar volume, so we still have to watch out a little bit. But anyway, with this now, we can say dE dt, we can differentiate this. We know how to differentiate these types of variables. So we can say dE dt, so the number of moles may change due to reaction, especially if it's non-equimolar. Our enthalpy may also change because the temperature is generally changing with time. So when we differentiate this, we've got the product of two, and in fact, these may also change. Your pressure can change and your volume can change. So we have to do our expansion like this. So we can first say, well, let's differentiate this and treat this as a constant. Then let's keep this as a constant and differentiate that. So the product rule of differentiation, you just go ahead and apply it and you can get that, right? And then you just stick this in the left-hand or the right-hand side here. So you just replace it over there. And now you've got a friendly version of the energy balance. You can get numbers for all these things here. Okay, so in the case of a Cstr, we can, of course, apply the perfect mixing rule. And also we have the balance for the Cstr. So we'd like to work with this energy balance and get rid of as much as we can that's more related to the material balance. And so we do that here. So for the material balance, and here again, we are writing the version, the unsteady state version of the Cstr. So we can go ahead and make the substitutions there, and we'll get another version of the energy balance. So that's the unsteady state energy balance for the Cstr. And so we can eventually show it's like that. So work through all the steps carefully, right? You'll find it's not an independent equation. So even though we did a fair bit of work to get it to the stage, still hidden behind RA is the concentration, which is changing with time. So you do have to solve for the concentrations as functions of time by solving the material balance still. That's okay. Right, and then there is this nice example here. So as I say, this set of notes basically is a tutorial and a set of notes because it's a set of case studies, right? So work through this example. It's basically the same as that development unsteady state Cstr. There's enough data given here that you can actually integrate this. So back then I was using MATLAB. I'm sure you like Python by now, so you can do that. Okay, here. Yeah, so here I'm making the note that sometimes you have to figure out what time function to use for your exit flow rate. So the problem above, I believe, has given the inlet and the exit flow rates. Sometimes you don't know the exit flow rate and you have to create a model that can be used to tell you what the exit flow rate is. So one simple situation is that your exit molar flow rate is the same as your inlet molar flow rate. So this is a simple case, and so you can easily apply this. So if you look at the balances above, you'll be able to solve those equations if that's the situation. Some other times you can't make that assumption. It might be that the reaction is not equimolar, so you are producing more moles than you are consuming. And in that case, you then have to think about what you can, what is staying constant in the system. So for example, if your pressure is a constant, right? So let's say we could assume that on average, the pressure is approximately constant. Then in that case, you can say, well, then considering what's in the reactor, if the pressure is low enough, if I can use ideal gas law, and if my pressure is constant, then if I differentiate the left-hand side, then dV dt, if that's constant, let's say it's a gas filling up the volume, so then dV dt is 0, and I'm only concerned with V dP dt. But I've said pressure is also constant, so then that's also 0. Then that only leaves us with R ddt nt, that's being equal to 0. So we can say this much, and then that gives us this relationship, right? The R can cancel out, and then we've got dn dt equals minus n over t dt dt. And then you can go ahead and look at your material balance. So you can write a material balance, and then you can say dn dt equals this thing. And so you can then substitute this into your, well, no, I don't want to substitute it into the energy balance. I can say that this equals this, Yeah, and then the F out is the thing we don't know. So there is a variable here that we don't know, F out. That's what we're trying to find, right? So now we've got this variable, this is known, and this is evaluated at each time interval. So we can solve for F out if we know dn dt. And then dn dt you can get from here, and you have to get it from dt dt. So you see, it's understood that we are solving dn dt and dt dt at the same time. So we are only talking about that we don't know how to find dn dt at the moment. We assume that we know how to get dt dt. So the unsteady state energy balance we showed earlier, we assume that we've solved that. And we normally think of dt dt symbolically, right? It's the rate of change of temperature. But it also is a number, right? At a certain instant in time, there is a given gradient in time, you know, and it's a number, 20 Kelvin per second, whatever. So this is a number also. And so we can look up the current gradient, the current rate of change of temperature as a number, and then the current number of moles in the reactor and the current temperature in the reactor. So we can solve this as a number, and then that will give us dn dt as a number, and then we can use that number in this equation to get F out. And once we've got F out, then we can integrate the balance. And you might be thinking, well, if you worked at dn dt, then why do you need to go and still work this out? And that's because you might be trying to solve a dni dt. You might be trying to solve for the rate of change of each of the species. So because you want to get dci dt, you want to know how the concentration of A and B and everything else is changing. So this is how, right? You have to first solve for F out. So you see, it gets surprisingly complicated very quickly, right? Number one, if you took this simple approach, there's nothing really to think about. Then when you are suddenly told, okay, only pressure is constant, and it sounds very straightforward, but then you have to do all these extra things just to be able to solve your material balance. So those are some of the complications that can arise in unsteady state, but it works, right? You can apply the solution, and I've done it in some of our research problems. This approach works. It gives you the right numbers, and you are able to solve the reactor balance. So that's one problem that may arise. And this one is talking about that you sometimes have to estimate Q dot. So hidden behind Q dot is that you have to figure out the heat transfer rate between your heat transfer medium, your cooling jacket or your heating coil, and so on. So you need some the temperature in the jacket, and then your current temperature in the reactor, right? The variable that you're solving for, that also occurs hidden behind here. So you have to unpack this term sometimes. Okay, and there's a nice problem here with the code given. This is in MATLAB. I wonder if anybody still uses MATLAB. Do you guys still use MATLAB at all? Maybe thumbs up if you use MATLAB. There's a time when I was accused of being a MATLAB fanboy. I used to use it for everything. Now, of course, everything is Python, and even JavaScript is pretty good. It rivals C++. JavaScript is actually faster than Python, but there are a couple of numerical issues you have to be wary of there. Okay, so no thumbs up for MATLAB. That's a pity. It feels like the end of an era. Anyway, here for the batch reactor, of course, we have been dealing with that as unsteady state all along anyway. So you are familiar with that, but what's a bit new is your energy balance also needs to be unsteady state now. And of course, this goes into here, right? In your reaction rate, you've got a kinetic rate constant lurking there. So to evaluate that kinetic rate constant, right, to get the K value, you need the temperature. So you are often solving a whole extra balance just to be able to update the K value in here. But in fact, and I'm saying it like it's a small thing, but actually that's the whole point of the reactor, right? That's why a reactor looks like a heat exchanger sometimes, because the reaction rate is so sensitive to the temperature. So it's worth doing all this. So for the batch reactor, obviously there are no flows in or out. So your energy balance simplifies like this. And yeah, you can acknowledge that the heat capacity dependence, and you can apply your mole balance on there, and you can find your temperature dependence like that, and you can apply it in your batch reactor. Right, so that's how you get the energy balance and integrate that with the material balance on the batch reactor. If it's non-adiabatic, if you are exchanging heat, so again, like we did with the Cstr, you have to add in that term, and that's basically it. Right, so that's it in terms, we have talked about this before. So last week we talked about when we are traveling around on that XT plane. In this case, we wrote CT plane, but it's the same thing. We have that maximum rate path line, and you can think about using initial heating to get onto the maximum rate path line quickly, or just let the system fall into the maximum rate path line and then control it onto that. So we talked about this last week, or the week before rather. Okay, so all that. Right, so that what we've talked about there is just in terms of deriving the balances. So in the set of notes, what follows after those general balances are a series of case studies. And here's an interesting one. This is a real world case. I think this was in Flixborough in the UK, where an orthonitrochlorobenzene reactor exploded. So this was the investigation behind that explosion. I think there were some members of the public that lost their lives in this explosion. So in terms of the investigation here, the energy balance was used to show the reasons for this explosion. And in the analysis, we look at on the day of the explosion and the operating conditions when compared with normal operation. So in this case, well, first off, the basic chemistry is this. So you've got the chlorine in orthonitrochlorobenzene. So the chlorine part becomes substituted with an ammonium part, and that's the product that you're looking for. And this is a highly exothermic reaction, as it says there, right? So there's the heat of reaction, strongly exothermic. And on the day of the explosion, your heat of reaction was actually a bit lower than it normally is. And that's just because I think we had a slightly higher concentration of the reactor here. So on the day of the explosion, you had a higher amount of orthonitrochlorobenzene, but a lower amount of ammonia. So on balance, you had a lower reaction rate, but your cooling was not sufficient to support this. So you had more orthonitrochlorobenzene. That means your reaction volume was greater. You had less ammonia, but you had a bigger reaction volume. So you had a greater volume. And it turns out that the amount of cooling water that was used in this case was not enough to deal with this higher absolute reaction amount. Right? Of course, your reaction rate is, if you like, it's an intrinsic variable, but then you go and multiply by the volume to get the absolute reaction rate. So that multiplier is bigger on this day. And so when you do the energy balance and you figure out the required heat removal rate, and you go and plot your temperature change, right? So this was normal operation. This is your conditions on that day. So you can follow through the details here, but this is basically what happened. Under normal conditions, if you are operating like this, and then if you switched off the cooling water, your temperature would rise slowly. and then your alarm system or your operator would say, okay, the temperature is going up. Let me bash in enough water and bring it back to normal temperature, and then I carry on as normal. On the day of the explosion, the cooling water was switched off, the temperature rose, and it went up slightly faster than normal. And then they tried to switch on the cooling water, and they found that it didn't restore to the intended operating temperature. The temperature just kept rising. And that's because you had a larger reaction volume, and the amount of water, the rate at which you could supply cooling water was not sufficient to bring this back to the normal operation. So it ran away and the reactor failed, and you had those injuries and even casualties. So that was the Flixborough incident, and this is the analysis behind it. Right. So that's case study 1. Any questions there? Okay, in the next one, this one isn't a documented case or anything, but you've got here multiple reactions. So you've got a case 2A goes to B. It is a strong exothermic reaction, and you've got a second reaction. So you are forming B in the first reaction and consuming B to produce C in the third reaction. And here you have possibly various dynamics effects from the interaction among all these species. So if you write your balances out, and I think in this case, it's a semi-batch reactor. So a semi-batch reactor does have you trying to maintain a high concentration of reactant by continuously feeding reactant. So if you like, it's a half Cstr. So you've got a batch reactor and your reactant gets consumed, but then you keep feeding reactant here. So it's semi-batch because it's not fully batch because there is this feed flow here. So you are feeding enough. So you are feeding at a rate which will restore your concentration. So your balances update. So you can read this in more detail to get your to complete your mass balance. And then if you follow the developments that we talked about earlier, you can update your energy balance correspondingly, and then you get the equations that you need to solve this. So if you integrate those equations, you can then show how the concentrations change with time and the temperature as well. Are you guys comfortable with solving ODEs and all that? I guess you've seen enough of that in your Python course, right? Applied computer methods. You must have solved ODEs there quite a bit. Right, so I think it's one of the Sci libraries that have a bunch of good ODE solvers. So you can use that. So Scikit, you can probably use that to solve ODEs. Okay, so that was a semi-batch. Then for startup and shutdown of a CSTR, so that's inherently unsteady state, right? Startup, you're not yet at steady state. Shutdown, you are going to move away from steady state. So you have to go back to this material balance. You have to use your unsteady state energy balance. So you can stick this in here. What's different? Oh, so this part is just trying to expand on this specific term. So it's showing your enthalpy, which is Cp delta T. You then have to unpack it like that. And so you can stick that back in, and then you get for your using your mass balance. So using dN dt equals all this, you can rewrite hi dN dt equals hi times each of those terms. And you can stick that in your energy balance, and then you get that balance there. Right, so for startup and shutdown, you get the balances for the CSTR, and then you can go ahead and solve. So here in the startup of a propylene glycol reactor, you are given enough information to solve that problem. You're given the volume of the reactor, and you can go ahead and apply all these specs to solve this problem. Right, and the solutions are shown there also. you'll find here that there's a nice stable steady state. So you can play around with the starting temperatures. You find it all loops back into a nice stable steady state there. Okay. And then there's another non-isothermal semi-batch case here. So all those case studies you can work through in the set of unsteady state operation case studies. Okay. All right, so that covers that section. And then what we want to do is get into the tutorial for the age distributions. So let's take a 10-minute break and meet again at 10 to 3, and then we'll carry on with that. Okay, any questions before we take a break? Okay, so see you all in 10 minutes.